In this video, we're going to wrap up chapter 23 by looking at t-test for a mean. So we're going to run a hypothesis test, and some key things to recognize is that we will be using the t-distribution again because we do not know the population standard deviation. So if our conditions are met, which we addressed in the previous video, we need to find our standardized test statistic, which works very much the same as a z-score. But you need to find your t-value. So you're going to still do your statistic minus your parameter, and that's going to be divided by the standard error of the statistic. So t is going to be equal to your sample mean minus your null mean divided by the standard error of the statistic. We would love to use the standard deviation, but we don't know it, so the standard error is the next best thing. So what we're going to do again is we're going to find the p-value by calculating the probability of getting a t-statistic that extreme or more extreme in the direction specified by the alternative hypothesis. And you need to make sure that you're stating your degrees of freedom, which is one less than your sample size. And remember, that's necessary because there's actually an infinite amount of t-distributions. So it's necessary to state that degrees of freedom. And other things to recognize, remember that the greater your degrees of freedom, the more normal your distribution looks. And actually, when you have when your degrees of freedom is equal to infinity, if you look in your table, you see that it is exactly normal. Okay, so easiest to understand by, I think, looking at a specific example. So the first one is the makers of Chips Ahoy claim that their chocolate chip cookies weigh 11 grams on average. Some hungry AP stats wonder if this claim is true. So they took a random sample of 24 Chips Ahoy cookies, and here are their weights. And there you have 24 raw data values. And do the data provide convincing evidence that the average weight differs from 11 grams? Okay, so if you were just reading this on the AP exam, I would hope that you would pick out that this is an average. So your brain needs to go, okay, so I'm going to be doing a test for means, and you have a sample. So you're going to run a one sample t-test. So what do we want to do? Well, we're going to state we want to test our null hypothesis of mu is equal to 11 grams, and we are not specified in a certain direction that these are heavier or lighter, so my alternative is just that it is not equal to 11 grams. We need to define what mu actually is, so where mu is equal to the true mean weight of Chips Ahoy chocolate chip cookies at an alpha level of, let's just go with 0.05. Now, in our plan, don't forget to name your test. So if conditions are met, we'll conduct a one sample t-test for means. So let's state our conditions. First of all, it must be random. A random sample of 24 cookies is selected. Next, I need to address the 10% condition. 24 cookies is less than 10% of the population of all Chips Ahoy chocolate chip cookies. And finally, I need to address the large counts condition. Now, I need to address the sample size. So I have no indication, first of all, of knowing that my population is normal. So then I go to the sample size, and I only have 24. That's not really large enough. I want it to be greater than or equal to 30. So I'm going to need to check a quantitative graph to see if there's any strong skewness or outliers. So I suggest you pause the video and enter your data into L1 and create either a histogram or a box plot or a normal probability plot. I'm going to go with a histogram. So once I make my histogram, I always adjust my bins in my window, which I showed you how to do in the last video. So it's easy to draw on paper. So my X scale is set to 0.5 and my starting bin is at 10 to create the histogram you see on your screen. And then I address the large counts condition by saying that the histogram of the sample data does not show any strong skewness or outliers. So since my conditions are met, I'm going to proceed with my one sample t-test for means. So you're going to get your sample mean right here, and you're going to need your sample standard deviation. So it's on to the do part. And in order to do this, I think probably the easiest way is to start by running your one variable statistics. Okay, so now I need to calculate my t statistic, which I get by taking my sample mean minus mu, which is 11, my population mean divided by the standard error, which comes from, take your standard deviation of your sample, 0.562, divided by the square root of the sample size, which is 24 different cookie weights. All right, so type that in your calculator, and I get 0.55. All right, so I'm going to sketch a picture as well. It's unimodal and symmetric, looking very much like a normal distribution, but I'm going to label this as my t distribution. And somewhere I need to state my degrees of freedom. So t distribution with degrees of freedom equal to, hopefully you can say it, 23, one less than your sample size. Okay, so if I'm going with a standard t distribution, 0 and then 1, 2, 3 away, 1, 2, 3 this direction. And I'm trying to see, for my alternative hypothesis, what is the probability of getting a t-value at about 0.55 is right here, or more extreme, or in the other direction, negative 0.55 or more extreme. So you can probably see already that this is not going to be a very rare occurrence. But let's finish this off, and I'm just going to label this as t is equal to 0.55, and over here t is equal to negative 0.55. Okay, so what else do I need? Hopefully you're seeing we don't have our p-value yet. So my p-value is going to be equal to 2, because I'm going to be doing a two-tailed test, times the probability that my t is greater than or equal to 0.55. So if you would forget that you need to double it for a two-tailed distribution because it's only, the calculator is only giving you one tail, the moment you go to do your calculator prompts, hopefully you'll recognize it. So to do this, you're going to go to second distribution, and you should be used to be doing normal CDF from our normal distributions, but you're going to do T-CDF, which is option 6. And the screen will look like this. So for our lower, because you're just going to be doing this upper tail here, is what this is giving you. You're going to put in 0.55. We're going to go add a bunch of 9s here, 9,999 standard deviations away from the mean is about as close to infinity as we need to be. Degrees of freedom you need to enter as, remember, n-1. Select paste, and you can see here is my p-value. So for calculator talk here, I'm going to write that this is 2 times t-CDF, and I'm going to label my different things, 0.55 as my lower, and 9999 as my upper. And I'll say degrees of freedom, 23 degrees of freedom. And that is equal to, I need to double what was on my screen, so 0.588, which is not rare at all compared to an alpha level of 0.05. So let's do our conclusion. Because our p-value, which is equal to 0.588, is greater than our alpha equals 0.05, so I've done that key part of comparing my p-value to my alpha, we fail to reject the null, two things that they will always look for in your AP response. Then we want a second sentence where you're putting it all into context. There is not convincing evidence that the true mean weight of Chips Ahoy cookies, I should probably say Chips Ahoy chocolate chip cookies. Now I'm not saying greater than or less than, I'm just saying differ, because it was two-tail. Differ from 11 grams. Okay, so there's my context. Think I have all my parts. Hopefully I didn't leave anything out in my explanation. If I did, of course, reach out to me. We're going to examine a one-tail test now, where, let's see. Human intelligence can be estimated using an IQ score. The distribution of IQ scores for the adult population is approximately normal with a mean of 100. Some students hypothesize that AP teachers have a higher mean IQ score than the general population. Well, of course we do. So they select a random sample of 10 AP teachers and record their IQ scores. Here are the results. So the first part of this is, do the data provide convincing evidence at the 0.05 significance level, so that's your alpha, that AP teachers have a higher mean IQ score than the general adult population? And then in part B, we are asked what type of error could have been made. So in order to answer that, we're going to need to, first of all, run our t-test. Okay, and why t-test? Because it's about means, and I do not know my population standard deviation. Okay, so I do know my population mean, or my hypothesized. So let's get going. So we want to test our null hypothesis where mu is equal to 100. And then we think, of course, that AP teachers are smarter, so we're going to say greater than 100 for the alternative, where mu is the true mean IQ score of all AP teachers using an alpha level of 0.05. Okay, so in our plan, if conditions are met, we will run a one-sample t-test. So let's go through our conditions. First of all, needs to be random. 10 AP teachers are randomly selected. Next one is my 10% condition. I would say that 10 AP teachers is less than 10% of all AP teachers. So finally, our large counts condition. You might be tempted to make a graph because our sample size is small, but hopefully you caught that IQ scores are going to be normally distributed. So we're going to say that the population distribution of IQ scores is approximately normal. All right, so our conditions are met. We can proceed. So I would have you pause the video now and enter your 10 values. Let's put them into L2, and we're going to run our one variable stat. Okay, so I just did that and I got a sample mean of 108.3 and a sample standard deviation. Varies by 9 point, I'll go 3 decimal places on this one, 9.4999. So I'm going to need, I think I just said one extra 9 there. I'm going to need my t statistic. So I do my sample mean minus mu divided by the standard error of the statistic, which is going to be 9.499 divided by the square root of 10. Take a second, type that in. 2.763 is what I get. And I'm going to sketch my picture here. I'm going to label this. Again, it looks a lot like a normal curve, but if you remember, just shifted everything here. If you remember, there's more area in either tails. It's a little flatter, so it's a t-distribution with degrees of freedom are equal to 1 less than my sample size, so 9 degrees of freedom. So if here is 0, here's 1, 2, 3 away, 2.763 is going to be this tail way out here. So I will label this value here as t equals 2.763. I want to know my p-value. So my p-value is going to be the chance of getting another sample of 10 teachers having that mean or higher. So the p-value is equal to the probability that t is greater than or equal to 2.763. It's kind of looking rather rare at the moment, but we're going to see how rare is it really. So I'm going to do TCDF. My lower is going to be 2.763. My upper, go a bunch of standard deviations away with 9 degrees of freedom. So if you're going to use some calculator talk here, you better label your values. Lower, upper, and my degrees of freedom. All right, paste, and that gives me 0.011. So yep, that's looking pretty rare to me. So let's conclude. So going to compare my p-value to my alpha. So because the p-value of 0.011 is less than alpha equals 0.05, we reject the null, and let's put it into context. We have convincing evidence that the true mean IQ score for all AP teachers is greater than the general adult population. Okay, so given our conclusion that we just rejected the null, what type of error could have been made? So if you recall the different scenarios, so in real life, either your null is true or your null is false, and you've either rejected or you've failed to reject. So this one here is your alpha. It's your type 1 error. Your type 2 error is this one down here. Remember, this is the power of the test. This is what you want to happen. And these two here, this is your beta, they add to 1. And this is just a correct decision down here. It's not necessarily what we want to happen, though. Meaning it's not really what we're usually looking for. So what type of error could we make? Well, we rejected. And if it were an error, it would be this scenario right here, a type 1 error. So we could have made a type 1 error where rejecting the null when it is true. And then let's put that into context. This would mean that AP teachers are not really more intelligent than the general population, but we incorrectly concluded that they are more intelligent. So just, again, think about how this could have actually happened. It's not that we made a mathematical error in our calculations. It would be that our sample that we drew is actually quite, it is rare, but it happens by just variation. So we have no way of knowing that we made this type 1 error, but it could have occurred. All right, the final thing I want to show you is how you can run this entire test on your calculator. So in the calculator, you hit Stat and then arrow over to Test, and it's your second option for a t-test. All right, so your input, you're given two choices, either data or stats. For this particular one, you're going to go with data, the first one that's highlighted, because you already have your raw data entered. So your mu of the null hypothesis is 100. Now, right here, L2, that's where I already stored my raw data. So if you have yours in L1, make sure you adjust it to that. I am doing a one-tail alternative. And you can calculate or you can draw. So I've done both. If it is a multiple choice question, this is definitely going to be your way to go. But if you go back and check what you wrote down from this video, these values do match. This is a good reminder also, like if it is an FRQ on the AP exam, you make sure you have all of these things labeled. You have your t-statistic, your p-value, your sample mean, and your sample standard deviation, and your sample size. You also need your degrees of freedom, which hopefully you have somewhere as well. Here's our drawing, and the one on your paper should match. Okay, that concludes this rather lengthy video. Please reach out with any questions that you may have.